Okay, good morning, everyone. Welcome to the second talk. The second talk will be by Indranil Biswas from Shivnadar University. He will talk about a Belyi-type criterion for vector bundles on curves defined over a number field.
Let me begin by thanking the organizers for the invitation to give the talk. So this is joint work with Sudarshan Gurjar. So let us recall a theorem of Belyi. Now we ask the question, when suppose you have a complex curve X, smooth, projective curve. So he asked when it is a base change of a curve defined over the Q bar, or in other words, when is X is a base change of a curve defined over a number field. So he came with the following answer, XC theorem. XC is isomorphic. I put a subscript SC because I'll be working with different fields. So just to indicate that this is defined by a complex number. Is isomorphic to the base change of a curve defined over a number field or same as Q bar, if and only if there is a meromorphic function f from X to P1 which is unramified right over CP1 minus 0, 1 input. In fact, it is in that case, if f is exist, it not only defined over Q bar, but you can check f to be defined over Q bar. You can check f to be. Anyway, so the remarks, one way is clear. This is from very old of work of Andre Weil. It follows immediately that if there exists f from xc to p1, says that it is unramified over cp1 minus 0, 1 infinity, then xc is defined over this from remark of Andre Weil, old papers from this follows. The point of Belyi is the converse. Contribution of Belyi. Converse is true. So this theorem become of interest, and just a historical remark. After some comments of Grothendieck, he pointed out that this produces an action of Galois group of Q bar over Q of certain set, and which is called like the children's sketches or something like that. So that's how it became. You get some space on which is the Galois group is acting. So that's why it became of interest, and there are many in the literature you can see. There are some of higher dimensional versions are there, but not so clean. But so our interest came from the following question. When is a vector bundle defined over Q1? So I have a criteria, there is a criteria for when a curve is defined over QR. So we are now trying to look at when is a vector bundle on this curve is defined over QR. So what is the data you have? We have by Bailey, we have this map. So let me explain the question a bit, because XC over CP1, I have curve which is unramified over 0 and our complement of 0 and infinity. And suppose I have a vector bundle EC. So by Bailey, we know that X is actually isomorphic to a base change of a curve defined over Q bar. And this map is such that this map is actually base change of a map defined over Q bar. Now we can ask the question, is there a bundle on the vector bundle on the curve defined over Q bar such that EC is the base change of that? The question clear? So I want to make the question precise because it can be twisted in a different way, so which may make sense different. So once we have this data, XC is X Q bar base change of Q bar. Now question, is there a vector bundle? What is the criteria for? Is there a vector bundle? Criteria that there is a vector bundle EQ bar over XQ bar such that the given bundle EC is a base change of EQ bar. Okay. So this is a precise question. So now, once you have this data and the bundle, the natural thing to do is to take, of course, you have a bundle and a map and the bundle on the top space. So natural thing is to take a direct image. Yes? So if a bundle is defined over Q bar, its direct image is also Q bar, defined over Q bar, right? So, and because the morphism is defined over Q bar. So it's a natural question which is first, is the criteria that F lower star of EC defined over Q bar, is it a kind of a criteria? The answer is no, of course, because there is a theorem of Grothendieck which says that any vector bundle on CP1 breaks into direct sum of line bundles, and those line bundles are just ON. So we know that F lower star of EC, take any bundle. No, I should not write F. Any vector bundle V on CP1 is direct sum of O, Ni, I from 1 to rank of V, where Ni's are integers. This is a theorem of Grothendieck, is isomorphic. So any bundle is defined over Q bar, right? If I take any vector bundle on CP1 is defined over Q bar. So if I put such a statement, it will be automatically true. It doesn't give any information that direct image is defined over Q bar. But a direct image comes with some extra data. So let me try to explain that. A direct sum index comes with some extra data, so I'll try to explain that. So let me go on parabolic bundle. It was introduced long time by Sheshadri, and it was much developed by Maruyama and Okugawa, and then there's a lot of work on that. Major work by, for example, Bicard, Mochizuki, etc. from different. So let us recall what is a parabolic bundle on curve, which is easier to describe. So I have M is a Riemann surface, and I fix some points, P1, P2, Pn. It's points. So they define a device as summation Pi, which is in this the definition of parabolic bundle, it is called parabolic divisor. So parabolic bundle is nothing but a vector bundle VW together with filtration over these points and some weights associated to the filtration. So take Pi, so you take WPi. It has a filtration. Maybe write it the other way around. Okay. I call this F naught WPi. So I take the fiber of W over Pi and have a filtration of subspaces. And for each, I have a number which is between 0 and 1. So this is lambda 0. I have to keep the point of lambda 0 I, lambda 1 I, lambda 2 I. Lambda ai I. And you assume that the numbers are non-zero and assume that they're strictly less than 1. So numbers will not play a role, but I have to, these things I said parabolic bundle, I have to describe it completely. That's why I put the number parabolic weights. It will not play, these numbers will not play much role in our discussion. So parabolic bundle is at each point have a filtration and weights. That's a parabolic bundle. Now, let me show, I want to claim that any direct image comes with a natural parabolic structure. So, there is no parabolic structure over where the map is unramified. It's only comes where the map is over which points of the target space over which the map is ramified. So let us to describe the parabolic structure. Let me just take a simple example, because it is a local question, the parabolic structure. Suppose z going to z to the power n from disk to disk. And suppose I have call it 5. The map 5, z going to z to the power n. And suppose you have a vector bundle on E on this disk. So now you can take the following thing. You take f lower star of E. No, sorry, phi lower star of E. Then it contains phi lower star of E tensor O D minus the divisor 0. Phi lower star of E tensor O disk minus the 2 twice the origin. So we have a filtration. So if it is n, I should go up to phi lower star of E tensor OD minus of n minus 1 of 0. I don't want to go to, we should not go to the next term because of what is called this projection formula. Because if I take phi lower star of E tensor OD minus n times 0, this bundle is pulled back from below. Because this is O minus 0, this is, so let me write somewhere. So this equality I'm writing somewhere here. So this is phi lower star of E tensor phi upper star of phi lower star of E tensor phi upper star of OD minus 0. This one n times 0. So this by projection formula, it is as phi lower star of E tensor OD minus 0. So you come back here. You started it here and you have just twisted by it. So you don't get any information by going further. So you terminate here, because that has all the information. So now you look at these bundles. They are all canonically identified outside the origin. So only thing they are changing is that the fiber at the origin. So this actually gives a complete flag, not complete flag. I mean, if E is a line bundle, then it is a complete flag. Otherwise, it's a complete flag in the sense that these are just strictly decreasing, and each time it is decreasing, the fiber decreasing by rank of E times 1. The fiber. So you get a filtration. This filtration of shapes will give you a filtration of the fiber. So you have in this situation, and then you give the number like how many times you have subtracted. So this weight you give n minus 1 by n. N is this is 2 by n. Up to this, it is n minus 1 by n. You give this weight. So that's how you get a parabolic structure on this map. Locally, every map is like this, so you can get in characteristic 0. So then this construction, though I did using local coordinates and etc., can easily be done without choosing any coordinate and disk. And this comes with a, this is a parabolic structure. So in general, you do the same thing. You have to be, I have only one point, right? So that's why it became easier. Otherwise, if this is a Riemann surface X, say Y and M, and you have to look at all the points over where the map is branched, and you have to subtract, you have to twist by 1, 2, 3, each branch point, and then, no, so these are ramification points. It's up, branch point is below. This ramification point, you keep twisting up to the order of the ramification, and then you get a filtration. If there are many points, writing down will be a little bit complicated, but you can easily see that point-wise you can do the thing and you can get a filtration. Parabolic bus. The parabolic structure. So earlier we observed that this is always defined over QR, but now what we have seen that it has a parabolic structure. So now we can state our theorem. I'll use the same notation in this. EC is isomorphic to the base change of a vector bundle over x cube r. So recall the question. Question was that given a vector bundle, when is isomorphic to a base change of a vector bundle defined over cube r? So I'm just trying to say that EC is isomorphic to the base change of the vector bundle over if and only if the parabolic vector bundle F was of EC. So usually a vector bundle with a parabolic structure is denoted usually by a star. That means usually star to denote, this is not a direct image, it's slightly confusing. The parabolic bundle is a bundle with extra structure. So the extra structure is usually the convention is that you put a star to say that there are extra structures. If there is a parabolic vector bundle is isomorphic to one defined over Q bar, 1 over x Q bar. So there is a parabolic vector bundle over Q bar defined over the curve x Q bar, whose base change is this, if and only if the original vector bundle is a base change of the base change of a vector bundle on x Q bar. Sorry, what have I written? P1 Q bar. Sorry, no. This is our Q bar. Okay. So look, CP1, but this is isomorphic to the base change of one defined over Q bar. This is our CP1, but the condition is that this should be isomorphic to parabolic bundle defined over P1 Q bar. If it is true, then if and only if then it is defined over isomorphic to. I have to always say that isomorphic to something. The original bundle doesn't make sense, it is defined over Q bar or not, because it is on a curve defined over C. What this meant by, our curve is defined over base change of a curve defined over Q bar. But that doesn't make sense to say bundle is defined. So it's isomorphic to something. Because there's a different question, that is the bundle is actually defined over Q bar. Okay. So now I'll give an outline of the proof. So we use a simple lemma which we crucially use, which is the lemma looks at first at sight it looks surprising because it's not doesn't look correct, but I'll state the lemma. And suppose I take M is a curve over. Here in this case, Q bar is not so important. M is a curve over Q bar, and E Q bar over M is a vector bundle. EC is a base change. Over MC. So the base change of the curve to this. Let V be a direct summand. What does that mean? This means there exists another vector bundle W so that the natural map E direct sum W to EC bar. EC, sorry, what I'm right, EC. Is an isomorphism. Is it a natural map? Is an isomorphism. So this is the assumption. Suppose I let W be a direct summand. This means this. Definition of direct summand. The conclusion, then V is isomorphic. I should emphasize the word. Various places have to use the isomorphic to the base change of a vector bundle defined over M. So I have a vector bundle on M. M is curve over Q bar, and this is a vector bundle over Q bar. I take the base chain. I take any direct summand. I claim that this is isomorphic to vector bundle, base change of a vector bundle. You see, one has to keep emphasizing this word because the bundle, sub-bundle may not be defined over Q bar, right? For example, you take O direct sum O on M. OM direct sum on this. So you get, when you base change, you get OMC. Base changing, base change. Now we have O sitting inside this, OMC sitting inside, mapping into this. Lambda goes to lambda comma pi times lambda. I can take the map, right? On the other hand, this is a direct summand, right? Because the other map, lambda going to lambda comma 0 is the, so there are two maps and their images give you decomposition. But of course, this sub-bundle given by this map is not defined over Q bar, but it is isomorphic to something defined over. So this word is important. So I am to clarify that this doesn't claim that the bundle is sub-bundle is defined over Q bar. Okay. So now how do I prove this? Its proof is very simple. Now one observation. A vector bundle on M over a curve defined over algebraically closed field is indecomposable. Here I am not writing XC or XQ bar because it's valid for all algebraically closed field. Okay. Is isomorphic. Now a vector bundle W1 on a curve, even projective array doesn't matter, is indecomposable if and only if what is meant by indecomposable? Indecomposable means it cannot be written as a direct, non-trivial way as direct sum of two vector bundles. Indecomposable, if it is written as a direct sum of two vector bundles, one of them has to be full and another has to be 0. That's the only way you can decompose it. That's a trivial way. There's no other way to decompose it. So that is called indecomposable. A vector bundle W is if and only if all automorphisms of all endomorphisms of W are of the form lambda times identity of W plus N, where lambda is a scalar element of the field, which is algebraic closed, which lambda is a scalar and N is nilpotent. So how do you prove this? You prove is clear. Suppose if it is indecomposable, take any endomorphism. Now look at its generalized eigenspace decomposition. Since it gives a decomposition of the bundle, since the bundle is decomposition, there can be only one eigenvalue, that is lambda. So suppose T is endomorphism. No, not T is bundle. A is an endomorphism. It has only one eigenvalue. Suppose indecomposable. Suppose W is indecomposable. Then look at the characteristic functions of A. This is a function, polynomial valued functions on the entire, on the base, and the base is compact or projective, so there is no non-constant function. So all the coefficient polynomials, coefficient of the polynomials has to be constant, independent of the point of the base. So it is a single polynomial. So it has the eigenvalues of A are independent of the choice of the point where you are looking. Identify for any point x of the base, eigenvalues of Ax are independent of x. And there can be only one eigenvalue, because if there is more than one eigenvalue, then generalized eigenspace will decompose the bundle. But the bundle is assumed to be indecomposable, so there's only one eigenvalue, which is called lambda. Let us call it lambda. Now take lambda times identity W. We know that this has to be nilpotent, because pointwise nilpotent, so it is nilpotent. Some power of the rank will be 0. Common term. So this one, the other way is of course obvious, because if it decomposes as W1 directs some W2, you take two constant lambda1 and lambda2, you multiply W1 by lambda1 and multiply lambda2 by W2 by lambda2, you get a endomorphism which is not of this type. So this is very clear. So now this shows that indecomposability, the condition of being indecomposable is independent of base change, because cohomology base changes, right? So H0 will base change. So if for one field, one algebraically closed field, all endomorphism of this type, if and only if after base change of this algebraically closed field to another algebraically closed field, the endomorphism remains same, so it has to be of this type. It remains same means just a base change. So this condition is it behaves well with base change of field. So therefore, indecomposability base changes. So if a vector bundle defined by Q bar is indecomposable, when I go to complex number, it still remains indecomposable. So now let me complete the proof before, so that we can make some remark. So now, any vector bundle run? Suppose B is a direct sum, and suppose write it that EC is equal to B direct sum W. I want to show that V is isomorphic to something defined by Q bar. So now write E, Q bar, the bundle on original bundle of Q, write is a direct sum indecomposable. Writing of indecomposable bundles. So now I base change it. So it becomes EC becomes direct sum I from 1 to n. BIC base change. So by previous remark, each of them is indecomposable. Now, I can now decompose V and W as indecomposable. So direct sum Vi, I from 1 to A, direct sum Wj, J from 1 to B. I write both of them as direct sum of indecomposables. So I have decomposes EC in two different ways as direct sum of indecomposables, here and here. Now there is a theorem, old theorem of Atiyah says that if you decompose a vector bundle into direct sum of indecomposable in two different ways, then each component, each direct sum is isomorphic. There is a permutation of the factors. The number of factors has to be same in two indecomposable decomposition, and there is a permutations of the factors such that one is isomorphic to the corresponding bundle in the other one, isomorphic. Let me state it. If a vector bundle F is direct sum Fi, I from 1 to M, and F is same, I write it as another way, J from 1 to N, F prime J, two-way decomposition, direct sum of indecomposable. A theorem of Atiyah says that M is equal to N, 1, 2. There is a permutation sigma of 1 to N, 1 to M to 1 to M, such that Fi is isomorphic to F prime sigma I for all I. Again, one should check, be careful to make the statement that Atiyah's theorem doesn't say that this subbundle will coincide with that subbundle. This is isomorphism. So now, here we have a direct sum of indecomposable. And now I can, on the other hand, have this, so I can write it as direct sum of Vi, I from 1 to A, direct sum, and W I decompose into indecomposable, J from 1 to B, Wj. So this is a decomposition into indecomposable because this have decomposed into direct sum of indecomposable, this have direct sum of indecomposable, and this is direct sum of indecomposable. So by theorem of Atiyah, each Vi is isomorphic to some Bj. So direct sum of Vi will be some direct sum of Bj, but Bj is a base change of something bundled from here. So V is a direct some base change of bundle from this. So now I just want to remark that this is algebraically closed is very crucial here. It's the only thing that's important, but it is crucial. For example, if you take R real number, you have the anisotropic conic, x square plus y square plus z square is equal to 0. This is a isomorphic, this is a smooth projective curve of genus 0, which is not isomorphic to CP1 because it doesn't have a RP1 because it doesn't have any real part. Now you call it curve y. So now y is, now you take tangent bundle of y and J1 of that. This is a rank 2 bundle on tangent bundle on y. Now when you base change it, it decomposes into the Z bundle on T of J1 of T of CP1 on CP1. This decomposes as O1 direct sum of 1. Rank 2 bundle, of course, it cannot be indecomposable. It has to decompose, but you know it decomposes this way. But this has to be indecomposable. Because if it is decomposes, then it has to be like this. And O1 is not a line bundle on this. Because if 1 is a line bundle on this, then using the linear system, you get a map from isomorphism from Y to RP and P1 defined over R, and you know they are not isomorphic because this doesn't have a real point and point defined over R, but whereas RP1 of course has point defined over R. So this whole thing is false if it is not algebraically closed. Even for real numbers, it's false. Okay, so now, so this is the lemma which will be crucially used. Okay, now I can start with the proof. I should not be, anyway, one way is clear, right? If the curve, as we started this, if the curve is defined of, yeah, it is the same thing is true. If it algebraically closed, then but in not algebraically closed, then stability is not preserved. For example, yeah, this is an example. This bundle on the anisotropic conic is stable, but when you base change, it is not stable. It's only polystable. Yeah, if it is, yeah. If you start, if something extension it becomes stable, the original thing is. So now, I should not erase the statement. One way is clear, right? If the bundle is isomorphic to on let us say X, and you have X cube and have the base change and have bundle over this. If it is isomorphic to bundle defined over X cube R, then it's and you have the map, right? And you have the complexification. If it is defined over some, suppose E is the base change, EC is the base change of E, then F lowest of the parabolic bundle, not just the bundle. You feel F lowest of EC is the base change of FC lowest. Let us call it FC. F lowest of E. So this parabolic, this vector bundle, suppose is a base change of this vector bundle. Then I start take the direct image, this parabolic bundle, and I take this parabolic bundle. So this is a base change of that. So if it is defined over Q bar, isomorphic to one defined over Q, then this parabolic bundle is defined over Q bar. I want to prove a converse that if it is defined over Q bar, isomorphic to is defined over Q bar, then E is a base change of bundle over Q bar. So X. Now I take the F, I take the Galois closure. So that means this map is ramified Galois. And that implies and X is Galois group gamma. So X is Y quotiented by gamma. Gamma is the Galois group. Let us give a name to this. Rho. Okay. So now I take base change of all this diagram. So I'll just Y will replace by YC, well, and you'll on right. So you take F lower star of FC lower star of EC on P1 Q. CP1. Now you apply rho upper star of F lower star of EC over base change of Y. So I started the bundle on XC. I push it down. That is given to me to be parabolic bundle, isomorphic to parabolic bundle defined over Q bar. I want to show that E is defined over Q bar. So all I do is that I pull it back to YC. So this is defined over Q bar, isomorphic to defined over Q bar. So this is isomorphic to defined. Isomorphic to 1 defined over. I don't have much time. I have to hurry then. I didn't look at it that track of the time. Okay, now I consider the following bundle. High upper star of E. I pull it back. Then I push and put down. So everything has parabolic structure. So direct sum pullback or direct image has pullback parabolic structure, pullback has parabolic structure. So now this is a property of pull forward and pullback of parabolic bundles, that rho upper star of lower star of some vector parabolic vector bundle F lower star. Suppose F lower star is a parabolic bundle on Y with some parabolic, doesn't matter. There's the divisor, that parabolic divisor is given. So the ramifications of this. So you take parabolic bundle, then you take rho upper direct image by this, go to P1, go to the Galois quotient, and then pull back. So now you have to understand the parabolic structure on that. Now you can do the following thing. You can just forget it. You can just take a usual vector bundle, right? But if you start with an usual bundle, this will acquire a parabolic structure. We saw that even a trivial bundle direct image has parabolic structure, non-trivial parabolic. This will have non-trivial parabolic structure. And you pull back the parabolic structure. The result is that this doesn't have a parabolic structure. The parabolic structure goes away. When you push forward, it has parabolic structure, but when you pull back by the Galois group, the parabolic structure goes away. In fact, it becomes the following bundle. G in Galois group, G upper star of F. This identity holds. So when you have a Galois covering, ramified Galois covering, when you start with the usual bundle, you push it down and pull it back as parabolic bundles. Then it is just Galois is twisted by the Galois element and the direct sum. So now this bundle and this bundle, I have two bundles. I have already showed that this is defined over Q bar. Now you can see that, but I want to understand what that bundle is. So first note that this is then naturally contained in this. Because I am starting from here, push it down and pulling back. And here I am pushing by the bundle, pull back of that, pushing down and then pulling back. You can see there is a just simple formalism. There is a this is in the natural inclusion. So this bundle, this doesn't have any parabolic structure. So this bundle doesn't have any parabolic structure. So now Now you can write down. So this is by this formula, direct sum G in gamma, G upper star of phi upper star of keys. Now, what is this subbundle? You can find out what is the subbundle of this. You take a subset S. It can be done more canonically, but I'm just, because I'm just up to a couple of minutes I have to say. Take a subset of S of the Galois group such that S to gamma quotiented by this Galois group of phi. Because this is Galois, so this is Galois. So this is an isomorphism, bijection, and identity element belong to this. You take a subset of, just a subset of this, such that it maps bijectively to gamma quotiented by Galois. The map is bijection and identity. Now, I don't have time, so I have to say, rush. So this bundle is direct sum G belong to this subset S, G upper star of phi upper star of EC. The big bundle is this, and this is a sub bundle, and this is this. This is a direct sum. Now the identity element is there. So that means if you put G as identity, you take phi upper star of EC. When you put G as identity, so this is a direct sum, right? Sum. So we already saw that this is defined over Q bar because this is given to be defined over Q bar. EC direct image, this is defined over Q bar. This direct image is defined over Q bar. That is my started. I want to solve EC is defined over Q bar. This is given to be Q bar. I want to prove that EC is defined over Q bar. Since this is what is defined over Q bar, this is defined over Q bar. So this is defined over Q bar. So this is, by the previous theorem, this direct summon is defined over Q bar. So now phi lower star of phi upper star of EC is defined over Q bar. I'm telling something wrong because every time I should say isomorphic to define the word Q bar. But I'm now, since I'm rushing a bit, I'm dropping the word Q bar. Now, pull back and push forward a bundle. Then the original bundle is automatically a direct sum of that because this is EC, because it is coming from below. So EC tensor with phi lower star of O of Y. Now this is EC, tensor phi lower star of OY decomposes as OX plus some another bundle. Because phi lower star of OY, when you direct image, you have the trace map. First of all, when you have a map from some gamma from A to B, so O of B, naturally it seems the gamma lower star of O of A. And when it is a finite map, then you can have an opposite map, gamma lower star of OA to OB. Because you take a point here, you look at the fibers and you are taking a function, you just add the function. So composition is degree multiplication by degree. So this splits, not in characteristic P, because if with the degree of the covering multiple of P, then composition is 0. Otherwise it splits. So it splits. So E star, EC is a direct summand of this, but it is defined over Q bar, so EC is defined over Q bar. Let's stop here.
Okay, so are there any questions on the speaker?
Yeah. Yeah, his bundle, yeah, that is, yeah, we did, Yeah, this we did. That's extension of summary. You can do two things. You can start with a bundle with fixed field, right? You can ask the same question. Right? You can do the bundle with a connection. So when you take direct image, etc., it will not have a regular connection, but you have a meromorphic connection. So you can ask the same question. You can ask for principal bundles. We could not do it for general principal bundles, but for example, bundles with orthogonal and symplectic structure, principal bundle, we could not formulate it well, so we could not do it. So that's the question. It will be, I think it is a natural question to what is the corresponding theorem for principal bundle. We could not, question can be formulated, of course, when is the principal bundle defined over Q bar, but I mean, the approach we could not, this is.
Other questions? Okay, if not, let's thank the speaker. Let's meet at 10 past 12.